back up. Okay. Very small inertia, very big inertia. All right, and let's see if you guys can see that. Yeah, you get a good idea there. All right, so I did just all this work tuning this thing and had it pretty perfect. So let's see where we're at. Okay, it did eventually get to 400, but there was some overshoot, some undershoot, and boy, it took a really long time. So let's do that same test. Let's go 400, and then let's go to minus 400 for 1 second and come back. So here we go. Well, that wasn't very impressive. So in essence, what we have done is we have changed the physical plant. We have added a bunch of inertia to our system. That changes all the tuning. So to optimize this, we have to change some values. So the first thing I'm going to do is go zero all this stuff out so I don't get fooled. And we're actually going to go way faster on this one because you guys are now experts. You know how this all works.
Let them shout the answers at you.
Yeah, we'll try that again. And so we're still going to do that too. Okay, we're now back to where I have no values, and so I am going to go put in we're going to put in 300, and this thing should not run. Bonus. All right, first thing I need to do is put in some F. Got to make this thing go. I got a much bigger weight on here. What do you guys think F should probably be? They're all thinking, oh, it's a trick question, I'm screwed. F was 1.35 last time. What have I done to change the drag on this system? Add more weight. So there's inertia, but is there that much more drag? It takes longer to spin up, but once it's there, not a lot more drag. And really, drag is what affects F. So let's try 1.35 and see what happens. Well, let's see, with 1.35 and only F, I told it to go 300 and we're going 295. Close enough. And as it turns out, the only real difference between that and that is the aero drag. And this is small, that's big, but that's all smooth, slick surfaces. There's not a lot of aero drag. Once it's up to speed, these look exactly the same. Getting up to speed is a whole different story. Also, imagine when we were doing the walk the line thing. We had our young lad, where are you at? What was your name? Carson. So Carson, our motor, we tell him, okay, you're really aggressive now. When we say left, you're going to go left violently. But then we add some inertia. We invite 17 of his friends up here and say, okay, climb on his back. And now we tell him, all right, when they tell you to go left, you go left in a hurry. He goes, all right, I'm all over it. Time to go left. It doesn't matter how hard he tries. We added a whole bunch of weight to that. He can't get anywhere in a hurry. Okay? We can be a lot more aggressive with P and when we tune this because he can't get away from us very quick. As you add inertia to a system, you have to get more aggressive with the values because it can't move very fast. So you don't run into an oscillation problem nearly as soon, but you need a much bigger hammer to get that thing going. So what we saw with this thing, we used our values before. It's stable. We didn't do anything to make it unstable, but we told it to go from plus 400 to minus 400. It took off, but it hadn't even gotten there, and it was time to turn around and come back. So this thing doesn't get there very fast. And the other key, when I looked and said, okay, you're going to go from positive 400 to negative 400, go. How much current did we use? I think it was about 15 amps. Well, I could put 100 amps into this thing. Why wouldn't I put 100 amps into it trying to get it going the other way? So when you look at something like this and say, is it stable? Yeah. Am I getting where I want to go? Not fast enough. I can probably do some more, and I still have physical plant left. I have current left. I have motor left to do more. So let's see if we can take P up higher. So F is about the same because my drag is the same, but I added a bunch of weight to that. That shaft can't change speed anywhere near as fast. So let's put our P in it.
Do you have any idea what the relative mass is?
Of that?
Of the two?
No, actually you'd think we would know that. We made this a year ago for this demo, and at some point we probably ought to do the math. That would be, it'd actually be useful. I would venture to say it's probably, the rotational inertia is probably 1000x. Okay. It's a huge, big difference. All right, so let's put P in, I don't know where we were before. We're going to start at 1 and see what happens. Okay. We got P in there at 1, we've got F in there, and so let's go look at a step response. And let's see, 5.
Here's a point where step response is handy because he can't grab that and make a huge change anymore.
Yep.
Yeah.
So we're going to do. All right, we're going to do a 1 second step response. Let me get this stopped. Okay. Couple of interesting things to observe. I still didn't get there, but remember last time we were only getting about 15 amps of current trying to accelerate it? I made P twice as big. We're 1 versus 0.5. And now I'm getting up to 30 amps. And so indeed, I am accelerating that a lot faster. And how stable am I? Looks pretty good. Don't have an oscillation problem yet. Good time to use more P. Now, if you remember last time, in the 2 range, it started to get unstable, and at 4, it went crazy. Let's see what happens. We're going to go crazy. We're going to go straight to 4. That was crazy land last time. It just oscillated and went nuts on it. So that's what happens if I program I as 4 and the integrator's all wound up. We'll try to actually change P. Yeah, that's how you fix that, isn't it? All righty. All righty, back to speed. And so now we're going to do 500 for 1 second. So now let's see what happens. Ah, now I was up to 40 amps and I actually got to speed. See, my error came down. My error actually got to 0 for a little bit before it was time to start slowing down. So I'm still stable. I don't have anything crazy going on here. I mean, when I finally get to speed, this is nice and stable. Cool, I made progress. Now, if we put 4 into this pulley, what happened? Crazy time. It oscillated all over the place. But when you have 17 of your best friends hanging on your back, you can't move very quickly, and you can put a lot more gain in this thing before it gets out of control. All right, so 4 was good. Should we do more?
All right.
Okay. Let's see. Who thinks we should do 6? Who thinks we should do 10? Who thinks we should do 14? Oh, they're starting to get scared. All right. For the sake of time, we're going to go to 14. Now that's a big heavy weight. If that shaft breaks off, if there anybody in this line better have their eyes open because it's coming to get you. What way is that actually spinning?
Yeah,
oh yeah, it's coming to get you, not me. All righty. So let's configure that to, and we're going to take P from 4 to 14. Okay, first interesting thing we know, we don't have any I yet. This is all P. What's my error? 1. Oh, pretty close. I may not even have to mess with I. And so this is a case where on a big inertia system, I can get enough P in there, it'll actually drive it to really close to the right answer. But let's see what happens to the step response. It might go crazy. All right, so let's see. All right, we're ready on the screen. You guys ready in case this goes crazy? All right. And okay, so remember, I set the current limit on this thing at 40 amps. So we're not going past 40 amps. I could actually crank the current limit up, and you would actually see this thing accelerate a little bit faster, and you would actually, this point, this would be a steeper slope. But we already see at 14, this thing is getting a little bit unstable. Okay? But if we actually let it run, it's still stable sitting still. So for giggles and grins, let's put some more P in it. What can happen? 100. And once again, for the sake of time, we're going to skip several steps. And I'm thinking 24 is a nice crazy number. All right, and so now I'm going to enter 24. Oh. Sorry, you're looking kind of unstable. Looks like a nervous Nelly. Looks like if you get close, might go crazy. And it is on the verge of being able to pick itself back up and figure this out. This is what you would call way over the edge. You have also got a big old inertia on here, and if I didn't have the current limit clamped on this, this thing would instantly run away and be banging into 100 amps going back and forth, and there would be fire and smoke relatively quickly. So we are indeed over the edge. And so if we say what might be good on this from a response standpoint, and we messed around for a while, we would actually end up back at 4. And if you go back and look, that's 4. I get my 40 amps. I'm getting everything there is to get with my current limit. And it's nice and stable and everything's pretty happy. And for that much weight, I actually get to speed in a pretty good time. We're at what, 6 seconds there? So yeah, we're a couple of seconds, I'm up to speed. Not bad, yep.
Because you got the current limiting on there, you're not going to be able to go up as fast as you can come down. So if you're in that asymmetric situation, do you really want to look more for the ringing on the down bumps?
Potentially, the answer is watch both. A lot of interesting things happen on the way to the dance, and just keep an eye on everything. It's a separate story. They do not capture the freewheeling current when the flyback diodes are picking things up, and so they only measure current that's actually on the drive side. And so it makes this a little bit goofy.
There's no active braking on this coming on the downside.
Actually, there is. And this is in a mode where when I tell it a different voltage, the fact that it's going faster than the voltage, it actually will drive current the other way. It does dynamically slow down. So it is what we call a full bidirectional servo. It's driving it to speed it up, and it's driving it to slow it down. And the dead giveaway of that is I'm putting 40 amps in to speed it up. This looks like less current to slow it down, but that's because half of this current is not getting measured based on how they do it. So if we were capturing everything, that slowdown would actually be bigger. See how that's steeper? Yes. That's because there's current that's not being measured here that's actually slowing it down. All right.
I think it's not under current control on the dynamic braking. It's only under the PID control.
Okay. All right. So we're going to say 4 is good for P on this. Keep in mind that's 8x of where we were on the little pulley. All right. So now let's do a little bit of I. Turns out we don't need all that much, but we'll dial in where we were last time, which I think we were 0.05. We're going to try 0.01. And let's come up here and check on our water bucket. Water bucket's got some huge freaking number in it. So guess what's going to happen when I turn I loose? This thing's going to go crazy. This time, we're not going to wait around. I'm actually then going to turn I-zone on, and you'll watch this thing clean itself up in a hurry. All right, so there's that. Whoop. Here's that. Way out of control. Here we go. And what you saw happen was the purple line was off in the O-zone. As soon as I turned I-zone on, it said, you're way more than 25 away from home. Empty the bucket. The bucket is empty. Only when I'm within 25 of being home do I then turn that back on to where it figures out what is supposed to happen. And lo and behold, if I look now, my speed error is exactly 0. I have no idea why I told him to go 284. That's curious. All right. So now we have a PI loop going. I could take I up some, it's going to oscillate. Turns out that 0.1 is about the right value. And if we messed around, that's what we would end up finding. All right. Now, big inertia here. This speed can't change very rapidly. D is to help us not overshoot. Well, this thing's going nowhere in a hurry, and I could actually put some D in. I could go up to 100. You really don't see a lot of effect. You really can't fix much with D here because this thing is not moving very fast. So D wouldn't gain you much. We could go through that exercise and you wouldn't see a lot of effect. Here, I would put a little bit of voltage ramp rate in it to just take the edge off. I want to keep this thing from violently changing from, say, 0 volts to 12 volts, and I want to slow it down just a little bit to be kinder to the system. And so I would end up putting just a little bit of voltage ramp rate. And keep in mind, it's not intuitive. The voltage ramp rate is how much the voltage can change per unit time. 1 is a really slow ramp rate because I can only change a little bit per time. A big number, and it goes clear up to 1024, is a really steep ramp rate, and 0 is no ramp rate, just goes straight up. So based on experience, I'm going to put in 100, and then we'll look at some waveforms.
What are you saving wear and tear on by putting more in?
You stop hammering stuff. Now, if you have got big inertia right on the motor, you can't really hammer anything. If you've got chains and all kinds of mechanisms that have lash in them, I'm just going to soften that attack so that I do not bang everything together until I have all my inertia helping me not go too fast.
So that's more applicable to like drive systems
yes.
rather than shooters.
Correct. And you can soften that onset just enough to not shock everything to death, and it doesn't really affect your performance. Now, as you put quite a bit of ramp rate in there, that screws up your loops. So you got to be careful with that. So,
Jared, what's the unit? What are the units of that number for ramp rate?
B, and I got to go reread this. I was talking to Omar the other night, and he's either changed this or changing it. It used to be, if you think back to that summing amplifier, you have a 12-bit output. There are 1,024 units equals 12 volts. The ramp rate value was how many ticks per 10 milliseconds I can change that. So if I put 1 in there, that output can change going from 1 to 1,000, 1 tick per 10 milliseconds.
I asked that question because if you look at the online API documentation, they say the units are volts per second.
And that is, I think, changed for this year. So you need to read that. It's different than it used to be.
So it might be a real unit then now.
Yes. And Omar did mention that the other night. What is unclear is when that transition took place.
This is supposed to be what's good. This is what's, I think they changed the firmware to the actual website.
All right, so here we go. We're going to play around a little bit. I've now got this big weight on here. I want to limit my thingy to 40 amps because I don't want anything crazy to happen. There's 100. Let's go to 500. Looks pretty good. Let's go to 50. That looks pretty good. Let's see what kind of dynamic range we have. Can we go to 20? Yep. Everything's stable. Let's see if we can go to 10.
Jerry, what are you changing right now?
Just as command speed.
Speed? Okay.
Yeah, so this is just closed loop. We're all tuned up, and I'm just commanding that to go different speeds. And one of the questions is, okay, it seems to work in mid-range. How much dynamic range do I have? I can go full speed. Can I go down 50 to 1 and have everything still work? Can I go to 100 to 1? Right now, I am 70 to 1. This thing will go 700 full speed, and I'm going 10, and it's happy and stable. I wonder if it'll go 5. And so with a properly managed loop, we literally, I think you can see it up there, and that thing will go 5,400 RPM. That's how slow it's going. Now, you are on the verge of what you can do here. But tuned right, you get pretty good dynamic range in the different speeds that you can run. All right, so that's what happens when you add a bunch of inertia. You can put a lot more P in it because it takes a lot more. Now, we'll do one more thing. Let's go back to 300. And let's go crazy. Let's see how it looks here. We hit it limited at 40 amps. I think 80 might be a funner number. All right, and so we are going 300. Let's go to 500. And indeed, I got up to 50 amps, but I started to get close enough to my speed that my P actually started throttling me back. So that's why you only saw 50 amps. You did see an impact. We were limited at 40 before, and all I did was change the current limit, but P started to get me back. Now, let's show you what's really possible. So I'm down to 100. I'm going to step it up to 600. So we got a big job to do here. Didn't do this at home. Hopefully it won't blow up. And indeed, I'm at 100. I need to go to 600. And I don't know where it went, but it's off the top of the scale. Let's find out here. And indeed, got up to about 70 amps before that actually was enough that P started to pull it back. So that's 70 amps going into that thing to accelerate. Now, keep in mind that's going through a 40 amp breaker. When I say I squared T and how breakers work, does that mean anything to anybody? Okay. Go Google an internet fuses and breakers. It's current squared times time is how a breaker blows. You can blow a breaker at its rated current usually in 10 seconds. At 1 second, you might have 50 times the current you can put through it. It's a thermal event. So I actually sucked 70 amps to a 40 amp breaker for a very short period of time. If we left that at 70 amps, in about 3 seconds, the 40 amp breaker on there would trip. Yes?
Now that you bumped up our current limit and your build guys were beating on you to be a little bit faster, would you go back and retune the whole thing?
Maybe. Oops. I would look and see, okay, before, at that lower current, how much was I convinced that I had convoluted the loop because I didn't have enough current. In this particular case, it accelerates faster, but we actually get to the right speed before we try to go back the other direction, so it probably wouldn't make a lot of difference here. But indeed, that is something to be considered if you want to hammer on a target. So that's big inertia. So for now, we'll actually leave that at 80 amps, and so let's do this. That's back going, so 100, let's do 600 for 2 seconds. So indeed, speeding up, I actually get to speed, my error gets to 0, time to slow back down. Slowing down, I actually pull 80 amps going down, and I get her slowed down and get my error back to 0, and okay, cool. So all that works, everything's nice and stable. So, let's screw with it. Let's add a bunch of drag. We could have put a big strap on this thing, but that gets hot. This is actually a fan designed to move a lot of air, and it's a big drag. It's just basically hanging a fan on it. Screw this down. I might actually be able to get away with just 2 screws.
Yeah, is there a safety capture around here?
Nope. To that point, you do have to remember, you got a battery with a lot of horsepower. You have big enough motors to move big weights in a big hurry. You do have to keep both eyes open all the time with this stuff because it will mess you up. There's enough horsepower to put fingers in gears and chains and cut stuff off. But you do have to be extremely careful. This will mess you up. All right. We now added a fan to this. And so for the sake of speed, we're going to do this. This will be relatively quickly, because then we're going to get to position control. This is going to get really interesting. Where are we at time? It's 3:20. All righty, and so battery 400. Okay, same inertia, but I've now added a bunch of drag to it. That fan is moving a bunch of air. And indeed, if I go and look, my amp draw free speed is a lot more than it used to be, and my F used to get me a whole lot closer to 500. And I added a bunch of drag to it, so I don't have enough F in it now to make it go the right speed. But interestingly enough, if I go 100, that fan's not doing a lot at 100. And, you know, percentage-wise, I may be a little bit closer. Still some drag there. So we're going to go back to, say, 500, and we're going to go dial F up a little bit.
You got everything else off?
I think so. I went back and changed it all. Yeah. And I'm going to guess that if I went from 1.35 to 1.45, that might be about right. And that gets me up to 475 to 500. So better. I could maybe go a little bit more, but I added drag. I could put some more F in it to make sure the PID didn't have to do as much work. The inertia is not changed that much. That weight dominates the inertia. That fan doesn't weigh anything. Turns out inertia heavily dominates P. P is basically going to be the same value. We could go through an exercise that we're going to find out 4 is the right value. So there's P. I pick up some more of my air. Turns out in I could put in my 0.01 that we were at. Turns out that fan actually screws that up a little bit. And when you mess around, you're going to end up back at about 0.008 is the ideal place for I. I also did not zero out I zone, so I zone is still live, and you saw it immediately clean up and take care of business. Okay? So now we're back PID, or I don't have any D in there. It turns out D won't help on this, too much inertia. So we're all tuned up. And so, let's say I want to do 100. And let's do a 500 pulse. And as it turns out, actually never quite got there. I mean, I'm still getting up to 65 amps speeding up and almost 80 amps slowing down. So I'm hammering this thing pretty hard, but it is pretty stable. So if I just do outright step responses, so let's just go to 500 and stay there. That's pretty nice. 65 amps to accelerate the motor. My air is coming down, my speed's going up. I don't actually undershoot. Things are actually pretty good. Could probably actually tune this thing a little bit hotter, but that's pretty stable and nice. And if I do a little bit of this, recovers pretty nicely, everything is stable, and lo and behold, I can tell it to do whatever speed I want. We're at 100, we're at 200, 300, 500, 600, 50, does it all, gets there quickly, nice and stable, away we go. And so that is velocity loop tuning. You saw doing it with literally no load. Tricky. You need a lot smaller values because that thing can get away from you in a hurry. As you put more load on it, your values get bigger. There's inertial load and there's drag load. And they affect things differently, and you've seen how you change the values to accommodate that. Also keep in mind, you put that thing up on blocks and tune the velocity for the wheels. You're all excited, it's all great, all the waveforms look good, and you put it on the floor and it runs like crap. Why might that be? Yeah, up on the stand, the inertia are those rubber wheels. It's nothing. On the ground, the inertia is, I have to accelerate the whole robot. I have changed my physical plant huge by putting that thing on the ground. So just remember, you got to tune this stuff and how it's really going to be used in competition. All right, any questions about velocity? Ta-da. All right. I'm back here. All right. So we did the sim coder, pulley load, we added drag, we added inertia. We actually did the drag and we did the inertia, we didn't do drag only. It's an interesting different set of numbers, but you get a sense from doing both of those. They're two different things. You tune them differently. P is about the same with the fan as it is with the pulley because there's no inertia there. But boy, F is different because you got drag and you end up with some other things different. You put them together, it's a combination of all that. So it's drag, it's inertia, think about what affects what, and a lot of it is just get a system set up, and I tell you, if you don't have a Saab set up, take your robo reel, bolt some stuff down, it doesn't have to be this pretty. Sitting at a bench where you can do this and get familiar with it, where you don't have a robot hooked to it, will help you get acclimated to this. And that's a pretty key element. Apparently there's some communications going on with the Joes.
No. You guys, he says Saab, that's system on board.
System on board.